We live in a time of global transformation. The Energy Futures podcast explores how we can accelerate the expansion of clean energy technologies and reduce our reliance on fossil fuels. From heating and cooling our homes to moving around our planet and beyond, we bring together researchers, scientists, business leaders, and communicators to exchange knowledge and try to answer one important question. How can we create a sustainable energy future for all? This podcast is produced by Energy Futures Lab of Imperial College London.
In 2025, the UK generated over 14 billion kilowatt-hours of solar electricity, enough to power more than 5 million homes. With solar tech evolving faster than ever, could the next leap in solar power come from labs pushing the boundaries of energy science? Today's episode is hosted by Christos Markides, a professor of clean energy technologies in the Department of Chemical Engineering at Imperial. He specializes in advanced technologies for recovering and storing thermal energy, particularly from solar and low-grade waste heat. His guest is Dr. Flurin Eisner, a lecturer and researcher in green energy and sustainable engineering at Queen Mary University. His research focuses on solution processable semiconductor devices for sustainable solar energy conversion and storage. In this episode, they discuss new solar technologies and their performance capabilities, a comparison between silicon cells and organic cells, using solar power for cooling, and the challenges in creating networks with renewable energy.
Well, hello and welcome everyone to another episode of the Energy Futures podcast. I'm Christos Markides. I work in the Department of Chemical Engineering here at Imperial. My research is more on thermal elements related to the solar energy field. I'll tell you a little bit more about that in a minute, but first I wanted to pass over to, I guess, my co-host or the person I will have in this conversation with, Flurin, to introduce himself.
I'm Flurin Eisner and I'm a lecturer at Queen Mary University, and I work mainly on organic solar cells, which is a new type of sort of photovoltaic technology that is still in research stage, but is hopefully going to come online at some point in the next 3 years.
Well, I guess if I can add something very quickly then on my background, I have personally been involved in a number of technologies, so have an interest in technologies, but not so much in the area that you work in. So I'd be very interested to hear some of the new developments in the photovoltaic field. But we've had an interest in one of the other aspects of solar, so let's say for heating, cooling, and potentially power generation using different types of technologies, power cycles, for example. Some people might be aware of CSP, concentrating solar power. I did potentially think that given how large PV is and you know its footprint in the kind of space that maybe we could start by just if you give us a bit of an overview in the way that you see it of the kind of PV field and what you think the technologies are there, what the options are for us and where it's going.
Yeah, I mean, I think it's worth probably starting just with, you know, how much energy that we get from the sun hitting the earth. So in the region of 100,000 terawatts, which is a measure of how much energy we get. While the sort of globally, the total energy consumption that we use is around 30 terawatts. So it's many orders of magnitude more energy hitting Earth than we currently use. So if we just manage to harness a fraction of that, that will already give us a lot of renewable power that we can use and sort of move away from fossil fuels. In terms of sort of current PV, so photovoltaic, how much we use at the moment globally. So we're at about 2 terawatts, which currently overall is about 8% of global electricity consumption is currently powered by PV, and that's a sort of a massive increase even in the last 10, 15 years. So it's an annual growth around 20%. So every year we're adding about 20% more PV capacity, which is obviously fantastic. But sort of the difficulty is keeping that up over the next 10, 15 years, sort of hitting those 2050 net zero targets really requires keeping that growth rate up, also increasing it if we can.
Yeah, that's a very good point. I've read a lot about this, and the growth rates of the PV industry have been tremendous for many years. I've actually seen in some years growth rates higher than 20%, which means that every 3 or 4 years we're sort of doubling capacity. I mean, my question as somebody who just peripherally has an interest in PV would be, do you foresee this growth at some point reaching any limits that would require us to move from silicon, which is, I think, the, traditional workhorse technology for PV? How do you see that evolving?
Yes. So I think it's worth probably just touching on. So silicon is sort of the 99% or 95% of all solar PV at the moment is silicon. It's been around since the 1950s, but really since sort of the 1990s, that's that sort of 20% growth rate that we've been talking about been happening. And the price of silicon photovoltaics has come down massively. And that's for a lot of reasons. Partly it's just capacity. For every sort of doubling of the amount of solar panels you produce, price comes down about 20%. And that obviously, if price is lower, more people buy PV. Also technological improvements. So a lot of technological improvements in silicon solar cells, including in the last sort of 5 years. There's been a massive shift from what's called polycrystalline silicon to monocrystalline silicon. And that really has increased the efficiency, so how efficiently they convert sunlight into electricity. And that's partly contributed also to that growth rate. So if you make the same product but it's more efficient, that's obviously great. And also in production, partly helped by the electronics industry, just producing silicon has got a lot more efficient, so we can make more solar panel for the amount of silicon that we put in. And that's also contributed to those price drops that we've seen. As a question of what limit are we at? So can we sustain that sort of improvements in silicon efficiency? So we're currently, in terms of solar modules, so big modules that you might put on a roof, I think anywhere between 20 and 25% power conversion efficiency. But silicon has a sort of an intrinsic limit, sort of a theoretic limit that we can reach, which is generally thought to be for silicon around 29%. So we're getting closer to that limit, and sort of to get sort of these further price drops. And there's a question of whether we need to investigate some other technologies as well.
So in terms of, you mentioned mono and polycrystalline silicon, which are the largest, I guess, global, in terms of people buying products, putting on their roofs, and also utility scale PV. So what's the current status of that? Are they roughly the same size as markets, or has monocrystalline now overtaken polycrystalline? What's the actual situation with those two kind of, let's say, competing or complementary options?
Yeah, I mean, 5 years ago, I think it was roughly equal, but now 99% of all solar cells that are being sold are monocrystalline. So there's been a massive shift because the price, it used to be too expensive to make monocrystalline silicon, but now the price has come back so much. They're more efficient than polycrystalline. So it's basically massively shifted away from monocrystalline, from polycrystalline to monocrystalline. Yeah,
that's interesting. I mean, this theme of very significant shifts over the last 5 years is something that we see across, I would say, the whole renewable space. Mm-hmm. Traditionally, solar was not the largest by any means. I mean, hydropower was traditionally the largest renewable energy form globally. And I think even 5 years ago, there was about twice as much wind as there was solar. But at this point, solar, which is dominated by photovoltaics, is between half and 3/4 of any renewable source of power being installed around the world. There are very, very quick changes happening. And it's good to see where we might be going. So what do you think about options beyond, so we spoke about silicon, so where do we go?
There's a lot of very, very exciting research going on. I mean, I will say that in terms of large scale, the bulk of new sort of capacity for, probably 20, 30 years is still going to be silicon, but there's a lot of exciting research and new solar cell technologies sort of around that, sort of trying to address some of the things that silicon can't do. So silicon has what's called specific band gap, so it can absorb a specific fraction of the solar spectrum. So we get the sunlight we get from the sun comes in different packets called photons, and silicon has sort of a fixed band gap where it can absorb a specific section of that, which is both great, but it's also sort of a limiting factor in some ways. And lots of these new technologies, sort of emerging PV, you can tune their band gap, so you can absorb different sort of spectra of those packets. And so there's various different technologies. So some of the most exciting ones are Perovskite semiconductors, and sort of the thing that I work on are something called organic semiconductors, and we can sort of go into a bit more detail if we like.
I've heard a lot about Perovskites. Yeah. I wish I could go back in my career and get into this field, but I can't. It's too late now. So yeah, can you tell us a little bit about that? As in, what are these materials? What makes them different? Why do they seem to have such good performance? And what are the challenges? Let's say from a practical perspective, I'm aware of things like stability and if I think that these are toxic materials, so we have to be careful of things like disposal and so on. But yes.
Yeah. So I mean, a perovskite is sort of a crystal structure, and it usually has a heavy metal like lead in the middle, and then sort of smaller elements around it. And you can tune sort of the properties of this material quite easily by changing some of those little elements around the lead, for example. So you can tune the band gap. And sort of some of the advantages, so to make a silicon solar cell, you have to get silicon, for example, from sand, and then you need to melt it down to really high temperatures, so above 1,400 degrees, for example, and then use various acids to purify it. While with some of these new technologies like perovskites, what you can actually do is you can just dissolve them in a solvent, and you've got this sort of spreadable ink that you can then use to process your solar cell. And you need much less material. So for a silicon solar cell, you need about 140 micrometers to absorb most of the light. So in that sort of region, while for perovskites or for organics, you need about 100 or to 1,000 times less, so on the orders of 1 micron, or even for organic solar cells, only 100 nanometers to absorb all the sunlight. So you need a lot less material, which is obviously great from a sustainability point of view, and you can process them at much lower temperatures. There's sort of two ways to process them. So it's called the solution processed way, which is the one I touched upon, where you dissolve it in a solvent, and then you've got an ink, and you can almost print it. There's been actually a lot of sort of exciting research where people put this ink into just sort of a normal printing machine for printing T-shirts, and you can actually just make a solar cell just through a sort of printing T-shirt press, which is quite exciting. And the other one is thermal evaporation, which is where you heat up the material, not to as high a degree as silicon, but you can sort of evaporate the material. And that's quite a nice process because we already know how to do that very well. So in our smartphones, the displays are made from organic light-emitting diodes, and these are thermally evaporated. So it's sort of a technology we know can be scaled very easily. And in fact, I mean, we spoke briefly beforehand, so some of the first commercial perovskite PV that I think was shipped by a company called Oxford PV in September, I'm pretty sure, I think they used thermally evaporated perovskite.
So it's good to hear about all these development in perovskites, and hopefully this will become a technology just like silicon that is widely installed and making a contribution. I guess from an end user perspective, could you tell us a little bit about, what would be the relative performance we could expect from these new technologies, and say relative to silicon, would we expect similar cost? Would that be a different cost? What would be the differences?
Yeah, so I mean, there's a big difference in what's going on the lab scale. So this is the sort of small scale things that researchers are working on. And in terms of those sort of power conversion efficiencies, perovskites are actually very similar to silicon at the moment. So up in the best perovskite and silicon are around 26%. For organic PV, so we're pushing 21%. But the difficulty is scaling it up onto a big scale. And silicon's very, very good at scaling up those lab scale efficiencies to sort of large scale efficiencies for a module that you put in your house. And there's also these emerging technologies are really struggling to sort of match silicon performance. But a lot of work going on to try and get higher. So one of the things that people have done in the meantime, which is exciting. So the first I mentioned the shipment by Oxford PV is to actually put a Perovskite layer onto a silicon, and that's called a tandem solar cell. And you can actually increase the efficiency of the overall module in that way, and sort of get past some of the intrinsic limitations of having a single band gap. By having two different band gaps, you can sort of increase the efficiency. And what that basically means is for the same solar panel that you put on a roof, you can get more power out per square meter. And one of the big limitations, I guess, for solar panels is they need quite a lot of space. And if you can increase the amount of power you get out per unit area, that's a fantastic thing. And there's other very exciting things. It's not just about efficiency, it's also about land use, as I say. And some of these emerging technologies, and that's also where organic PV is very exciting, is you can make them onto, so the first thing I mentioned is the sort of tunability. So you can make them different colors and you can make them to match specific applications. So one sort of quite exciting area of research is agrivoltaics, is where you use solar cells at the same time as growing food, for example. So if you, for example, think of making a solar cell that lets through all the light that plants need to grow, and then the rest of the light it uses to generate electricity. So you can imagine sort of putting them, for example, in a greenhouse where you have sort of dual use, where you can grow plants whilst simultaneously make electricity. And that means you don't need to use some other area that you might want to use for solar panels. So sort of doubling the amount of land use or halving the amount of land use that you need. Building integrated photovoltaics is also a very exciting area of research for these new emerging technologies. For example, making windows that are transparent, because we want windows to be transparent, but using some of the light that we can't see, using that to generate electricity. And that's also something that silicon can't do because it's got this fixed band gap, while with these other technologies, you can change the band gap so that you can basically make them different colors. And then the final thing that sort of differentiates them from silicon is you can make them, as a very lightweight, you need a very small amount, and the low temperature processing, so you don't need to heat it up to very high temperatures, also means you can put them on flexible substrates like plastic. So you can make bendable solar panels, you can fit them to curved surfaces, you can also make them very lightweight. So for example, you can carry around a solar panel with you. And actually, another thing that sort of stems from the spectral tunability is you can use them for harvesting indoor light. So traditionally, silicon solar panels on a large scale used to harvest solar light, but silicon, especially crystalline silicon, is not very good indoor. And by changing the band, it can actually make some of these new technologies much more efficient indoor. So if you used, for example, a pocket calculator, and you've just got these little solar panels, that's usually amorphous silicon. But amorphous silicon is not very efficient. And you can get, usually about 10%. By using some of these new technologies like Perovskites and organic, you can actually push 30-40% efficiency. And as our lives become increasingly interconnected, we've got more and more devices that we need to power inside. For example, I don't know if you've heard of, for example, the Internet of Things, where we've got all these sensors around our houses that constantly measure things and need power. And if we had to have if we had to recharge them all the time, that would create a lot of problems in terms of battery usage, in terms of plugging them in. So having these indoor PV is something that's quite an exciting target application for them.
You've mentioned a lot of things. But before I ask you some more questions, I wanted to focus a little bit more on what you mentioned in terms of the manufacturability of these types of modules, these newer technologies, and you mentioned you need less material. You mentioned that the intensity of the process is lighter. Yeah. One of the criticisms or critiques of not just solar energy, but a lot of the renewables is that that you have to, in addition to other things, factor in the sort of embedded energy and the embedded carbon. So, we talk about 20%. In reality, it's not 20, it's less than that because it's not operating at 25. But also, there is a sort of a penalty that you've paid to get the sort of module there in the first place that you're hoping to recoup over the lifetime of your technology. And I don't know whether you could, drill a little bit in, because I suspect that you must be doing much better with respect to this kind of payback in some of these newer technologies compared to silicon, which requires all this energy, high temperature heat, so on.
No, it's a very good point, especially if you're installing terawatts, worth of power or tens of terawatts. The embedded energy becomes quite important because you need that up front, and often that's so from fossil fuels. You basically take the energy from fossil fuels to make PV, which obviously is not ideal. And for silicon, I think the sort of payback, the energy payback time, so the amount of time it takes for the solar cell to sort of give you more energy than you put in to make it, is, depending on where you are in the world and how much sunlight there is, between 1.5 to 3 years, sometimes 4 years in sort of far latitudes, which is not bad given that a silicon solar panel lasts for 25, 40 years, right? So, yeah, exactly. But it's still energy you need to put in, and it is a lot less for some of these emerging technologies. So there's a company that makes evaporated organic solar cells in Germany, and for their product, I think they estimated it takes about a month for an organic solar cell to pay back the energy that it takes to put in. And that's with that organic solar cell being a lot less efficient than a silicon, but it just uses so much less energy to put in that you need to put in that is a lot less. I don't know what the exact numbers for Perovskites, but I'm sure it's much lower than the 1.5, 3 years, probably in the order of a few months as well.
So 10 times less. We might use a term order of magnitude, but say 10 times less than silicon. And it's a very important point because it goes to the heart of some of the not criticisms, but I guess genuine questions that come up when we're talking about technologies, right? They don't just come out of thin air. They're a result of a manufacturing process, which can itself be energy intensive, and it can be fossil fuel based. The other thing I just wanted to mention very briefly, because I've personally had an interest in this, is that, of course, there's a difference between, let's say, generation and capacity. So you mentioned at some point 20, 30%, these kind of efficiency values. I think what's important for a lot of people to understand is that this is what the manufacturer will tell you. This is what the tag will say on the panel when you buy it. And typically how they do that is they will test the module at what they will call standard conditions, right? So they will say, we have 1,000 watts per square meter, which is a reasonably strong solar intensity that you would find maybe in the middle of the summer in London, midday. So quite a significant amount of light, and also at 25 degrees. Mm-hmm. And one of the challenges that I personally had an interest over the years is that if you have 1,000 watts per square meter landing on a panel, it's impossible for you to be at 25 degrees. You'll probably be at 60 or 70. Now, that penalty that you pay in going from 25 to 60, 70, or, if you're in the Middle East, if you're in the Mediterranean, somewhere hotter, you might be in excess of 70 degrees, can be very significant, as you might be losing 20% of what you would expect to have at 25 degrees. And this opens up a huge space in terms of research interest. So there are lots of people purely in the PV space looking at how we can reject this heat. So we don't want the heat to be trapped in the PV cell because we want it to cool down. We don't want it to heat up. And then there's a completely different community that sort of takes the view that, not competing, complementary, that takes the view that, okay, you did mention at some point a need to be mindful of space, right? So yes, 20% of the energy of the sun will become electricity. What happens to the other 80%? Because energy is conserved. Well, the other 80% is just rejected to the atmosphere in some way or another, right? Either whether through radiation or convection, it's just lost. And so the view would be, well, a house doesn't just need electricity, it needs electricity and heat. So the global demand for heat is about 2.5 times what is required for electricity. And so the view would be, well, why don't we try to, we've got all this heat that we're going to reject. Why don't we try to recover it and deliver it? It might be useful. Now, this is easier said than done because the value of heat, I think everyone will understand that the value of heat is not as important as the value of electricity to us. The quantity is large, but the value per unit quantity is low. But still, there are some opportunities in terms of how we can trap the heat rather than just throwing it away and then utilizing it and then providing, recovering it, providing it to someone. So this type of technology is called a hybrid PVT, hybrid PV thermal collector. It looks like PV. It sounds like PV. And if it does, well, it's got cells in it, and you have some kind of component. It looks like a panel. You've got some component where you pass either water or air. And what's interesting about this is that you've mentioned building integrated PV. So there's BIPV, and then there's BIPVT. So they try to integrate these types of collectors that can generate electricity and maybe recover a bit of heat and make it available to the building by somehow integrating it with the envelope, right? So facades, the same thing you would do with PV. And I think there are some very nice opportunities there, but it's a difficult area to be in general. And I'm not talking about myself, I'm just in general, because I think most people understand that the decarbonization of heat is generally more difficult than the decarbonization of electricity. And that's why, by the way, I think the facts speak for themselves. That's why we've made so much progress in decarbonizing our electrical grids over the years and less progress on decarbonizing heat because it's a harder thing to do. But there are some areas there where I think solar technologies are slowly starting to make inroads, and they're directly connected to PV. And then, of course, all sorts of technology options that don't have anything to do with cells, and they're just about trapping heat from the sun and providing useful thermal energy to people.
Do you have a sort of idea of what sort of extra efficiency boost, I guess, you can get by also capturing some of that heat that is usually lost?
Yeah, it's a very good point, and it's there's a sort of a zeroth order answer, a sort of a simple answer, and then there's the devil is in the detail type discussion that we might want to have. But so for normal temperatures, so one of the characteristics of heat is that so we've mentioned that PV cell efficiency deteriorates with temperature, so it drops. But it doesn't drop as much as the thermal efficiency of a solar thermal collector does with temperature. So the efficiency of every solar technology deteriorates with temperature, because at higher temperature you just lose heat, or in the case of PV, have a deterioration in your performance. But for normal temperatures, let's say, so that I can give you a rough idea, you'd expect to get something like from normal, not advanced lab stuff, maybe 2 to 1. So you'd get 2 units of heat for 1 unit of electricity. You'd get better at lower temperatures. You get worse at higher temperatures. And I mean, in terms of the ratio, because you will, as your temperature goes lower, you gain a little bit of electricity and you gain a lot more heat. And as your temperature gets higher, you lose a little bit of electricity and you lose a lot more heat. So it's a tricky one, but in most building applications, there's of course there are many uses for heat and many different types of heat demands, but the one which is dominant is heating and so-called domestic hot water, which we know is around 50-60 degrees. So for these sorts of temperatures, you'll be looking around 2 to 1.
Okay. I mean, there's also, I guess, the added benefit as well. I mean, the issue often with PV is that it will generate most power when the sun's strong, which is usually when people use the least amount of energy. So you need to store the electricity in some way. But I guess with this system, you've got the added benefit of being able to store the hot water, or the thermal energy is a lot easier to store than electricity to some extent. That's
right. So, most thermal-based technologies, when you try to incorporate the storage element to them, benefit from this, because storing heat is always easier and more affordable than storing electrons per unit energy. I have to say, though, as kind of disclaimer, which is that even though it might sound like you're increasing your overall efficiency by a factor of 3, so you go from 1 unit to 3, 1 plus 2, as I said before, it's not really fair to just add them up because 1 unit of electricity and 1 unit of heat are not the same thing. Yeah. And so, it becomes a little bit complicated in this field once you start having heat and electricity, and what's the best way to say that I've got this and how much is that increase and so on. It's a little bit more complicated. But just bringing it back, yes, so heat is easier to store per unit energy. And in power generation, for example, from thermal technologies, so at least we have something that does the same thing. So we have, let's say, utility scale PV, these large solar farms with many, many rows of panels everywhere. The equivalent would be, there are many technologies, but you might have seen parabolic troughs. You might have seen these sort of big towers in the desert with mirrors pointing and very bright kind of part of the tower at the very top. So they're generally more expensive, of course, and they're a much smaller market than PV. They've been growing, not at 20-25% that PV has been growing at, but they've been growing, and they are projected to grow. What tends to happen with those technologies is that they will it's much easier for them and more and cheaper, let's say, to get them to operate in inverted commas 24/7, because you can store the heat in various ways. And then at night, you can just have that heat going from the tanks to kind of continue to drive the what's called the power block. So this is the part of the system that's responsible for taking that heat and converting it to electricity. So that's where their main advantage is, this kind of affordability of operating for longer durations.
And I guess I don't know much about this, so it's quite interesting. So also, as PV continues to grow, do you think actually the market for those sort of things actually also increase? Because if you have lots of your power system dependent on the sun shining at one particular point, that also puts pressure on having technologies that can create renewable energy that sort of can store that energy more, sort of release that energy at different times.
Yeah, absolutely. So you're right. As we have more and more renewables penetrating into the grid, and there are some projections that by 2030, which is not that far away, we'll have tripled or close to tripled, very close to tripled solar PV capacity relative to, I think, 2022, which is, if you can think of it, it's just incredible to say something like that. But as you have all these renewables going into any national grid, you create problems for yourself that are hopefully the topic of another podcast, so we don't have to go into those. But you require storage, so you require what's called dispatchability, the ability or flexibility to provide that energy when you need to. And storage becomes more and more important. And so there are some projections. Now, these might be controversial. You have to be careful who's making these projections. But so the argument would be that, yes, as PV takes the bulk, right, of the market, and therefore the bulk of the generation, slowly we're going to move into sort of a space where having something that provides the storage and is able to turn up and down like we want to becomes more and more important. Now, you can do that with PV. Of course, there's no reason why you can't have storage. Lithium-ion is a fantastic technology itself. Costs have come down a lot over the years. But it's even cheaper to do it with through thermal means. But of course, we said CSP, concentrating solar power or otherwise. The problem there is, and this is, I guess, one of the general challenges of working with the sun, is when you're relying on concentration, you need to go to regions of the world where you have good quality sunlight. So you will not find a CSP plant in South London anytime soon. But there will be parts of the world, I think you were kind of alluding to this, where it would make increasing sense to start installing some of these systems that have the capacity, the inherent capacity for storage, which is affordable. And yes, there are some projections at the global. So if we add this sort of global picture, not at a national picture, but as a global picture, that CSP will sort of start to gain on PV, but in the long run, once PV has reached some level where we need to think about storage. And yes, so there are some projections that say things like this. I don't know if they're true, but
it's very difficult to predict, isn't it?
It is very indeed. Yes, one of the the $1 million question, I guess, right?
Yeah, I mean, I guess that also comes back to with PV as well. I mean, not even taking into account some of those things. One of the biggest challenges is actually distribution, where you want, because of the intermittency, you want PV to be as widely distributed so that if it's not shining somewhere here, it's shining somewhere else, and you can take electricity from there and take it to there. But there's a big problem, I guess, with grid capacity, and sort of interconnecting different countries is actually very good. I mean, if we could take, if we can install loads of PV into Sahara and then take all that electricity and take it to Europe, I mean, that would be ideal. And the sun's shining a lot more than it is here.
So maybe it's time to mention desert tech then. So I'm old enough to remember grandiose plans. A great idea, by the way, but a massive undertaking. And for those who are maybe watching this and are not aware, I think this actually started mainly as a CSP project. So mainly this kind of thermally generated electrical power from the sun. But it branched out over the years. So at some point, there was a mix of CSP, PV, bit of wind. And the idea was if you can put a number of plants in this kind of North Africa, Sahara-type region where land is not really valuable in some sense. You don't need it for agriculture or other purposes. And then you have high voltage DC power lines transmitting the power to Europe, then that would be a very nice solution. It failed, but I don't think it was on technical grounds. I think it was more on the need to find investment. And I think this is maybe a case of right technology, wrong time. I mean, it was a little bit early. I want to say maybe 20, 30 years ago now. Yeah. You're probably also aware of this. I don't know what the most recent version of this
I'm not sure what the most recent version is. I just know, I know there's a big investment into solar in Morocco, I think mainly it was, and didn't quite take off. But I guess there's chronic underinvestment into sort of power networks. I mean, I know about the UK. I mean, it's a big difficulty also with wind, taking the power generated by wind in Scotland, taking it down here, for example. So I guess that's how all these questions of sort of PV and renewable energy generation are very much linked into the wider sort of electricity network as well.
It is true. I mean, there's this criticism of renewables, which I think is a fair criticism, that they are diffuse. I mean, I don't think anyone would doubt that. Fossil fuels, we've used them for a reason. They are a very condensed, easy way to generate energy at a point when you need it. But renewables have this disadvantage that, as you say, right, so the energy is in space and time scattered around. Sometimes you have wind, sometimes it doesn't blow, then you might have sun somewhere else you don't. So just to give, I guess, people a rule of thumb, renewables in general, and I'm talking very broad brush, over the whole envelope of renewables, globally you're looking at something like, say, 20% capacity factor. And a capacity factor tells you what fraction of the capacity of your system you're actually generating energy. So 20% of your 20% efficiency you're getting, the other time it's nighttime, or you're not, and that's quite low. But okay, this would improve with storage, and storage is a very important part. So capacity factors improve with storage, and they improve. And we've been talking a little bit also about these thermal systems. Yes, thermal systems rarely. And there are some, but rarely these CSP projects come online without storage. So you'd be looking at anywhere between 3-4 hours of storage to things like in excess of 20 hours. And this, again, to improve the capacity factor. So sort of to improve, another way of saying that is, let's say the fraction of time that you can operate your system working at some level and it doesn't sort of shut down because the sun isn't there. And I think you're right. Over time, this will become more and more important. Since we're on the topic of things other than electricity, there's an often forgotten element of the energy problem, which is cooling. So if you go electrically, of course, then, okay, there are technologies we know, electricity driving air conditioning systems and so on. So we know that there are conventional technologies to do that. And a lot of people are working on this. But it's not so much on the technology level. It's more on control, integration. But there are some interesting options to go directly from solar heat directly to cooling without having to go through the electricity intermediary, right? It's a challenging area because some of these technologies have been around for a long time. Some of them are new, some of them are more mature. It's always a cost issue, so you have to factor in the usual, cost, maturity, complexity, the size of the system. One of the advantages of PV is that it's very highly scalable, right? So you can have a single panel for your house, and you can have 100 or 10,000 panels. It's a very scalable system, whereas some of these thermal technologies they don't scale like that. So you have very, very strong benefits when the system gets large, but it's very difficult to make it small. And that's why your calculator has a little PV cell on it, and it doesn't have a little tower with a... So, yes, I think so. Cooling is often forgotten, but it's becoming an increasingly important, let's say, energy vector in its own right.
Absolutely. In some of the PV technologies as well I talked about earlier, actually that's one of the things that organic solar cells will be quite good at as well, because you can tune their band gap, for example, to only absorb infrared light, which is where what heats up rooms. And for example, you can make a solar cell that, again, you can integrate into windows, because often windows are where a lot of the heat comes in. So you can make a solar cell that you can put on a window that only uses the infrared light. So you'd get cooling effect, for example, in hot countries, while also simultaneously making electricity. That's also quite exciting. So that'd be probably more useful in very hot countries. It wouldn't be very useful in the UK. But if you have sort of a building with lots of glass and they heat up massively, if you can use some of that thermal energy, that's again to generate electricity, but then you wouldn't actually need to cool the building in the first place, because or cool a lot less, because a lot of the thermal energy would be sort of absorbed by the solar panel.
Yeah, absolutely. It's a very nice area, by the way, light management in general, because light comes in from the sun at different colors. You were mentioning before, packets of light, and whether you want to see it as photons or wavelengths or, let's say, colors, right? And you can do different things with different colors at the same time. And it's a very exciting area. You could be, as you say, you could be using a different material for your photovoltaic conversion, or you could be using a conventional material and then have something else absorbing the infrared, so it doesn't, because the infrared is a part of the sunlight that most people associate with heating, right? Yeah. You can sort of block that with other ways. And I think these are very, very exciting areas in research. From your perspective, I guess it would be a challenge to identify nice materials that absorb and convert the right part of the solar spectrum to do what you want to do, and how you tune that, I don't know. You can tell us more?
Absolutely, yeah. I mean, with organic solar cells, so the organic and organic solar cells refers to a material made of carbon and hydrogen atoms, so a bit like plastic, but you convert it into a semiconductor, and through chemistry, so it's from organic chemistry, you can basically build whatever molecule that you can come up with. The challenge is finding the right molecule, but through changing the molecular structure, by adding carbon atoms, taking them away, you can sort of almost infinitely tune the properties of your semiconductor. So you could, in theory, make a very good semiconductor that only absorbs infrared light. In practice, obviously, it's not as difficult. You've got the synthetic chemistry restrictions. You've got knowing what molecule to build, and but there's a lot of that's where the research lies, in terms of synthetic chemists working together with physicists, with engineers, and trying to build the perfect semiconductor that does So for a certain application, that's sort of the exciting part of these new emerging technologies.
I guess it's also important to consider those trade-offs in your conversion efficiency, right? Because from first principles, with my basic knowledge, I know that there's a sort of a sweet spot in terms of what you want to be doing when you're trying to convert sunlight to electricity. And then now you have these interesting challenges where you say, well, yeah, maybe I don't really just care about that. I want to try to do something else. But as soon as you try to push this kind of conversion region away from this sweet spot, you have maybe some limitations coming in. So that brings in interesting questions about, okay, what is the sort of overall optimum? Because here I'm trying to do multiple things, right? I'm trying to generate electricity. I'm trying to cut down light. I'm trying to get some heat or whatever it is. And I think there are some very nice problems there. Is there a sort of a structured way in the field to identify what you're trying to do with the molecule, or is it more sort of trial and error, how does the community progress in terms of what are we trying to achieve in terms of our band gaps or
Yeah, I mean, a lot of it is trial and error, although I'm sure, synthetic chemists will tell you. I mean, synthetic chemists are amazing. They've got this, to me, is always amazing, this intuition of, I'm going to put a carbon atom there and I will do this. And to me, that's always amazing. But they've obviously got a lot of experience. I mean, at the moment, there's a lot of interest in using AI to try and sort of, screen lots of molecules and then try and extrapolate from that what the next best molecule will be. There's lots of issues with that. I think it's sort of partly trial and error, but also a lot of knowledge going into that as well. Sort of, I don't know, call it informed trial and error, I guess. And I get a lot of the work that I do is trying to, if I get a molecule from a chemist, is trying to understand why it works or why it doesn't work. And then I guess that feeds back into the synthetic chemists. This didn't work because of this, so I'm going to try this because I know this will happen. So it's sort of a conversation between different chemists, physicists. I think understanding is always really important, trying to understand why something works, not just, this doesn't work, I'll try something else. Mm-hmm. Trying to figure out what it is. I think also, that's in any area of science, that's sort of a fundamental thing that I guess often gets overlooked by, policy experts, and where do you put the money? That's where fundamental science is, really important, because otherwise you're just sort of grabbing in the dark.
Yeah, I agree. You've made an interesting point that I can relate to, but in sort of other areas, of course, which have to do with the difficulty that you have. Let's say, you come up with a nice new material, right? But if the volumes are not there, now, okay, PV has the volumes, but I'm talking generally. You come up with a nice material. If you don't have the volumes to justify the need to set up, the new plants to make this new type of material that we didn't have before, it's actually quite a difficult sell. Because, yes, you might get a benefit, but does that small benefit outweigh the investment that society needs to incur to switch from, whatever we're doing to the slightly better version? It's an embedded, we have an inertia as a society. We do some things, we have processes, we have industries that are set in a certain way. It's very difficult to just, wipe the slate clean and say, oh, we'll do something else now.
Yeah, I mean, it's in terms of PV, yeah. The UK has got some of the highest density of fantastic research going into PV. So it's really it's one of the best places in the world to do PV research. But in some ways, now a lot of the fundamental research has been done, and sort of funding has moved on to an extent. So PV in the UK is actually not funded that well anymore. And so that perception that the hard work's been done, we can now move on. But I think in many ways that's an error, because you miss all those next things that come along, all the new improvements.
Yes, that is a tricky one when you have leadership. And by the way, I don't know how many people realize the global position that the UK is in with respect to not just PV, but in general. And I would say not just in terms of academic impact, but most people don't know. And I often try to make this point that within Europe, the UK is the third largest installer of PV. Many people realize this. So the largest one is Germany, of course. Everyone knows about Germany. The second one, which kind of makes sense and you would expect because it's somewhere south, is Italy, right? So we have now a large country with pretty good footprint in the Mediterranean, so lots of sun. And the third one is the UK. So we had some very nice days last week. And I was looking at generation. Yeah. So that's just capacity. That's just, how many, let's say, panels you've got installed, right? So Germany, Italy, UK. But in terms of generation, I was looking last week at how much power was coming from PV across Europe, and it was Italy, UK, Germany. Really? Yes. So, we've got slightly better conditions than Germany. They're sort of close, there or thereabouts. But again, I think it's just people don't understand, or sometimes I don't believe it. How far we've come. I mean, who would have thought that the UK is generating this second greatest solar PV generation in Europe, 2025. There you go.
Yeah, no, some of the sort of policy decisions as well going forward are quite exciting. I mean, I think in the next 2 years, all new homes have to have solar panels installed on them, which is, I don't know why we've not been doing that for, the last 20 years, but it's exciting that it's now being done. Because it's just, a roof is the perfect place to put a solar panel in terms of where it's facing. It gets as much sun, gets the most amount of sun, and no one uses a roof, so you're basically getting a space to put a solar panel for free. So,
I have this anecdote, this funny story, which is we did a study in this must have been a little bit more than 10 years ago. At that time, a UK story. At that time, there was something called a feed-in tariff. So we were paying people to export electricity from their homes to the grid. And the feed-in tariff was 43 pence per kilowatt hour. Okay? So I remember publishing this paper. A very good student of mine, Maria Gerando, she might be watching. So she did this work, 43. So all your economic analysis and, but does it make sense to do it? Am I making a profit? Is it very difficult? How many years is it going to take me to pay back this system? It was a PVT, by the way, but still the electrical part was being sold. And I remember 3 or 4 years later, right, I looked again at the feed-in tariff, and it was 4 pence per kilowatt hour. And just this, again, this kind of goes to show you how quickly this space has moved, how much progress has been made. Something that needed 43 pence per kilowatt hour, 12 years ago, suddenly is, on par or even cheaper in terms of some of the cost to conventional generation. And you're right. It's something we can easily do. The challenge is what we mentioned before, which is that as you have more and more people putting PV panels on their roofs, you'll start having more and more stability issues that these we can deal with. These are engineering problems. They're not insurmountable problems, but they're problems. They're challenges for us to address. So we're going to need that storage. We're going to need to be careful in how we design our networks. It's a new type of experience for us. We haven't traditionally operated networks with this amount of renewable power. And so I think with that, we've slowly come to the end of our conversation. I don't know if you have any closing remarks.
No, it's amazing that, PV is the cheapest form of any form of electricity there is, and we should be making as much use of it as possible.
I think the proof is in the pudding. The revolution has happened.
Yeah.
We're no longer projecting anymore. No. It's a positive story. It's a nice story of success, and let's hope we continue along the same lines moving forward. Thank you. It was very nice to meet you, and I enjoyed our conversation.
Very much. Thank you.
Thank you for tuning in to the Energy Futures podcast. Here at Energy Futures Lab, we are dedicated to addressing global energy challenges through pioneering research, innovation, and advocacy. To learn more about us and the exciting projects we are working on, visit our website and follow us on social media. If you enjoyed this episode, Please like and share and subscribe to stay up to date with our latest content. Until next time, stay curious.